Hello and welcome. This is analysis of a gas refrigeration cycle. If you're familiar with the Brayton cycle, this is basically a reversed Brayton cycle. Also, it differs from vapor compression system. Like from 2 to 3, it's not a condenser anymore. Actually, it's a heat exchanger. And similarly, there is no evaporator as in a vapor compression system. From 4 to 1, where the cooling takes place, it is also a heat exchanger because gas don't evaporate or condense. They just exchange heat with the hot environment here and the cold environment here. So this is where the cooling takes place. So this is one of the desired variable, the rate of cooling. And the net power input is, of course, the compressor power minus the turbine power generated. So let's go. I already have analyzed the problem and put it here. If you have the schematic next to you, state 1 is very simple. They have given us everything basically. The temperature is 10 degrees Celsius. This is the inlet to your compressor. Pressure is given. And we have selected the ideal gas model. That's just to show you where it is. If you go to thermofluids.net, I've already logged in. So if you go to the test steps, to find the correct test step, you go the specific open branch, and vapor and gas refrigeration cycle is here. And you can pick either the PG model or IG model. In this problem, they asked for variable specific heat, so IG model should be picked. But because the temperature variation is not much, either model will produce almost same answer. We can verify that. Okay, so state 1 is quite simple. Everything is given. Even the mass flow rate is given to us. So state 1 is found. State 2 is isentropic. State 2, so S2 equals S1 because compressor exit is isentropic to compressor inlet and the pressure is given to us. Mass flow rate is the same. State 2 is found. State 3 is the condenser exit. Again, for that, we know that pressure doesn't change and the temperature is given to us, 50 degrees Celsius. It's also the inlet temperature to the turbine, and mass flow rate is the same. So this state is found. So this is also the inlet state of the turbine. So the exit state of the turbine is state 4, which is isentropic. As you can see, entropy must be same as state 3. And the pressure must be same as pressure at 1 to complete the cycle. Mass flow rate is the same. And that completes the calculation of this state. If you go to the graphics panel, just as you can think of, it's a reverse Brayton cycle. If you draw a constant pressure line through state 1, here comes one constant pressure line. And if you draw one through, say, state 2, here's another constant pressure line. Let's go to the device panel and already set up the devices. Device 1 is our compressor going from 1 to 2. This way, W dot external is negative. This is the condenser. Heat is not condenser, I'm sorry. This is the heat exchanger, I should say, instead of condenser, where heat is rejected. And the heat is rejected, that's why it's negative. Device 3 is the turbine. Will produce some power, net power, between state 3 and 4, which will be less than what the compressor requires. And that difference will be our net power. Again, if you recall, device 1 is our compressor. It needed 13.26 kilowatt of power, and the turbine is generating 9.57 kilowatts. So there's some net power requirement to run the system. And device 4 is, of course, the heat exchanger on the cold side. So 4 to 1, this is where the heat is absorbed from the cold place at the rate of 6.35 kilowatt. If the question is what is the ton of refrigeration, you can convert the unit and find the answer. Cycle panel obviously puts everything together, and we got all the w.net is here. This is how much power is given, net power is required. It's negative because it's required. The COP of the refrigeration system is found 1.719. Just as I said, just suppose we used you wanted to use the PG model. Then you can do a super calculate, generate the test code, Control A, Control C, and go to, test step for open refrigeration cycle, PG model, and load this test code, the IG model. And when you load, everything is recomputed, but this time the PG model is used, as you can see, and we expect the answer not to be too much difference. Look, it was 1.719 before, it's like 1.7108, so COP hasn't changed much, just like the net power, because the variation of specific heat with temperature, which is accounted for in the IG model and not accounted for in the PG model, doesn't create that much of a difference because temperature variation is not so high.